So, welcome everybody. This is ETC's AV over IP Web Task Force. We've been doing a series. We're going to continue with a cadence of doing a session every 3 weeks until we've got our next annual conference at NC State. And today we're going to be graced by Steve Bogart from Atlona. He's got a good deck on network technology, kind of dig into the tech for the first time. We've talked about some terminology and we've talked about some requirements, and this will actually be, charts of system topologies and discussions of differences and communication protocols and things like that. So hope everybody enjoys that. And really, without any further ado, take it away, Steve.
Thanks, Jim. Yeah, this one is kind of intro to networking, right? So some of you, this may be really kind of a lot lower level than you're looking for, but hang on, we do get into a little more complex stuff towards the end of the presentation.
And this really sets the stage for some exciting and quite in-depth sessions that we've got for the next 2 or 3.
All right, let's get going. All right, so networking and AV over IP. So one of the most critical elements of working with latest AV over IP is knowledge of the data networking, understanding how to connect these things up. In an existing network, keeping AV and other data sets separate is critical, because if they get connected together, bad things can happen, especially to your enterprise. So first, let's go over high-level elements of networking. This will give you an understanding of the essentials. It's important to point out that these do not compare to those formal data networking training certifications like what I took, CCNA. And if you're thinking about taking CCNA, feel free to reach out to me. I can give you some pointers. It is the first test I ever took in my career that I did not pass on the first try. If you're in the IT space, hope you understand the impact of AV over IP on your network. These all consume network bandwidth, and there needs to be a deeper understanding of network principles. So first, let's start off with the type of networks. When you're talking to IT professionals, you need to know what type of network you're talking about. First, there's the local area network. Local area networks confined to a geographical area, could be a building, could be as small as a classroom. Next is the WAN, or wide area network. These go beyond the building, can cover a city, state, country, or even the world, as networks can be connected up for enterprises across the entire globe. VLANs are what we use to create separate, different parts of a network. AV systems are usually on their own VLAN, so they won't interfere with traffic being used for business application. Dante AES 67 and Network AV over IP all use VLANs. So many IT professionals and equipment will reference what layer it communicates on. Basically, you need to understand the first few layers from a general AV perspective. Open System Interconnection, or OSI model, calls this physical layer. These are cables, connectors, and pinouts that are used. The second layer, or layer 2 of the OSI model, is a data link layer, also known as the MAC layer. Third layer is the network layer, which deals with communication at routers and switches. It's where you manage the network traffic. The OSI model has a total of 7 layers, but we'll really stay on the first 3. When I was taking the CCNA class, they talked about all 7, but really for what we need to deal with, it's the first 3. TCP/IP model is a simplified version. As you can see, it combines the first 2 layers to deal with network access, the cables, the connectors, the MAC addresses, and that's what you need to access the network. And to simplify the concept of layer 3, they also call this the internet layer. This will be important when we discuss specifications for switches when you're installing AV on the network. On layer 2, we mentioned the MAC address. Every device globally has a unique MAC address. This is also how manufacturers can use auto discovery, because those first 3 octets are unique to each manufacturer, and usually the last 3 are serial number. But everything communicating on the world, on the internet, or on the network has to have a MAC address. It's a 48-bit number expressed as 6 groups of 2 hexadecimal numbers, separated by a hyphen or colon. The first part As I mentioned, it's the manufacturer. Second part is the serial number. It does vary somewhat by the manufacturer. A NIC is a network interface controller contained in the interface physical port that connects to a network. It's usually integrated with the main circuitry of the device, so like a laptop can connect with a physical cable and wirelessly. That would have two NICs. It's also important to realize when you connect up to a switch that has an Ethernet port, you may be using your network device or your network MAC, but it also could be using the switch's network MAC, which comes into play when we talk about security, because if everything that plugs into that device, be it like USB-C, suddenly gets to share that NIC, now you have different devices that all use the same MAC address. If you're using MAC filtering on the network, that can cause a problem because someone with malicious intent can plug into the network and get a known, thought to be good MAC address. IP addresses. This is like a phone number. It's how the device talks to another device on the network. So our wireless connection, our laptop, can have one IP address and the wired connection can have another. This means just one laptop device use two IP addresses. To find the IP address on your laptop, you need to access the command prompt. Command on Windows or on Mac, it's ipconfig. At the command prompt, use the ipconfig. On the Mac, it's ifconfig. IP address is a set of numbers separated by a period. We call each of the number set octet. Each octet can be a number from 0 to 255. Without getting too deep into the understanding, the first set of octets are called the network portion of the address, and the last two are called the host. Subnets. So subnets and subnet masks are basically how you can figure out how many devices can go onto that particular network. So in this example, we have a 192.168.100 IP address, subnet of 255.255.0, and a gateway 192.168.1.1. Basically, the 255 tells the IP address that it must match the gateway with no deviations. Look at a simple IP address and the common subnet of the 255.255.255.0 and gateway of .1. This means that the IP addresses on the network must start with 192.168.1. something to match that gateway. Now, I said the addresses could be from 0 to 255. However, there's a couple reserved addresses. 192.168.1.0 is called the network address, and 192.168.1.255 is called the broadcast address. Neither of these can be used as a device on your network.
Hey, Steve, we didn't pregame about questions. You want to take them as they come or save them to the end?
You bet. If you've got questions, bring them on.
So Kevin Hartman had asked, what exactly is the difference between using a VLAN and using a subnet? Is it that one uses MAC or one uses IP or something else?
Yeah, so VLAN is separating all traffic. You could have like a VoIP VLAN, right? So you could have multiple devices that are on multiple networks. They're all in the same VLAN. Subnet is going to be restricted to just those devices talking to each other. After that, you need to have a router.
And I'll add to that, a subnet in a simple network is talking about things that are locally connected. It's a physical arrangement of devices that are adjacent to each other. A VLAN is a logical arrangement. So you can have devices that behave like they're next to each other, but they could be on different switches and routers down the line and in different locations.
I guess I need to pull up the chat so I can see the questions as they come in.
That's it so far, but I'll keep you honest on them.
Oh, excellent. Okay. So public versus private. So there are four classes of IP addresses, class A, B, C, and D, and E, which is actually 5. These are a number of specific range by the IANA, Internet Address Numbers Authority. They've determined certain large enterprises could have the first set of IP address. So when the internet first started, General Electric got the first octet of 3, and AT&T was given 12. Simply put, we're not supposed to use these ranges, but at the same time, they're assigned these numbers and assign the default subnets, but that's literally out on the internet, right? So inside the network, we could, not really necessary. Simply put, it limits the number of available IP addresses to just over 4 billion, which when I was coming out of college seemed like, gosh, how could we ever get over 4 billion? And then I was talking to a guy that was designing for an auditorium, and I said, hey, you're having students and all these guys come in. How many IP addresses are you designing for? And he said 10 per student. So if you figure an auditorium holding 100 students, that's 1,000 IP addresses. That's a bunch. So in an effort to slow down the use, the segmented parts of A, B, and C network IP addresses, these ranges are now private. So in other words, they exist only on your network. And then when they get out on the public internet, it gets changed to that public IP address and routed that way. So you'll probably see on every network a 192.168.1 dot something, or it could be another one that's popular is 192.168.0 dot something. And depending on the subnet mask will depend on how many addresses are in that network. Next, what they did was change the way that private networks used in home and enterprise to talk to the internet. When you connect to the router, it uses a NAT, a network address translation, to convert your private network into one of the public IP addresses. To find the public IP address, all you have to do is type a browser and type in, what is my IP address? So just type in, what is my IP address?
Maybe pull out the on my computer part and Google.
Yeah, right. What is my IP address? Public. So my public IP address is 72.47.186.54.
And that would be your modem or your gateway or your ISP connection in whatever facility you're in, not necessarily what your computer thinks it itself is on your local area network.
Yeah, so if I go to, mine's a little weird because I've got a bunch of different networks, but 192.168.1.21 is my physical device. So even with the public and private split that we had out, you're gonna run out, right? So that's why IPv6 came out. We're actually already starting to see some devices with IPv6. In fact, all of your mobile devices, AT&T, Verizon, T-Mobile, Total Wireless, pick your carrier, are all using the new IPv6, which is a whole lot harder to call out. But that is a bunch of addresses. I forget what, 4.3 billion now? And that's just on the public side, not counting private network devices. And they would then use the translation for the public routing. So the way you physically connect a network device together is known as topology. Which topology you use will determine how information flows through the network. If you're connecting two devices together without the need of a switch, you're point to point. Also could be HDBaseT, right? That's similar to a network technology, or SDVoE. All of those can be similar to network and are point-to-point connections. When all the nodes are connected to the router or switch as a central point, this is called a star topology. A lot of times when we're doing AV systems and we do them on what's called an island, that would be a star technology, right? Where all the devices connect to that one router and switch, but they don't necessarily connect to the enterprise. Router is a device that shares a single internet connection, like I just showed you on mine, with multiple wired connections, or could even be wireless. It serves as a hub or firewall, providing multiple ports for computers, game consoles, media streamers, and more. It also has a port dedicated to communicating with the modem, or for me, it's Sunlight. A Wi-Fi router or wireless router is a device that shares a single internet connection with multiple wired and wireless devices. A wireless router can have up to 8 external antennas. Which model you pick could be internal, could be an external, it could be both. Wireless gateway is a device that functions as a cable or DSL modem and a router. Typically includes several ports on the back for wired connections, and the Wi-Fi antennas could be internal or external. Fooled me, Jim. I thought there were questions coming in. It was just you asking a question. So Wi-Fi. So defined by the standard of 802.11, now there's a bunch of different 802.11 standards, right? From no letter and then all the way up to AX. It is continually being revised and redone. It's technology standard for over-the-air interface between wireless clients and a base station, or between two wireless clients. 802.11 has a number of different iterations that have to do with speed. The current specification that have come out in the last few years are AC and AX, also known as the 5 gigahertz range. These have greatly improved wireless technology and the number of devices that can talk to an access point simultaneously. If you're not running a 5G at your house, you probably should. Some considerations for these devices would be interference with walls and other devices, and some are using the same wireless channels. So earlier we went into great detail about IP addresses. These IP addresses can either be dynamic or static. Dynamic IP addresses are given out by a DHCP server, or a server that reads that MAC address, remember that unique address that every device has, and assigns it to an IP address from a pool of available addresses. The DHCP server will allow devices to hold an IP address for a period of time. It's also called the lease time. After this time, it usually automatically renews if the device is still connected. The last part of the IP address is the gateway. The gateway is usually the topmost router in the hierarchy of routers. The gateway has the special duties. It passes out the traffic to all the other routers and helps resolve DNS, or domain name resolutions. A DNS resolves the domain names such as google.com, right? So google.com is what we know it as, but that's not actually its IP address. Usually there are two types of DNS, internal and external. It is used like a search domain. Another segment type is MDNS, which is a multicast DNS. These services allow devices to discover each other with an IP address or without configuring a DNS server. And the all-beloved network time protocol is a protocol designed purely for the transfer of accurate time around a computer network. We use this a lot in AV over IP, especially in Dante. The protocol allows clients to accurately synchronize time and do that with a precise reference clock. Ports, right? You don't want to just communicate on any port. Several ports are registered. These are just a few. Port 80, HTTP. Was originally the web port, right? That's where all web addresses. Now we've kind of transitioned to HTTPS, which is the secure side of the websites. When you're internet surfing, especially like out on the public internet, you want to always be sure you're using the HTTPS. When I was doing my CCNA wireless certification, the instructor taught from a hotel, and so we did the class in the day, and at night we played white hat hacker. So what that meant is we basically put up a wireless access point, named it the same as the hotel wireless, and then we forwarded traffic back to the wireless network. And then we could literally see in clear text all the stuff going from HTTP sites. It's becoming less and less of an issue as most stuff is secure, but yeah, definitely can be. Oh, I don't know. Jim, do you know if there's a difference between PTP and NTP?
Getting the precise words to tell you accurately right now. PTP is precision timing protocol, so people will use that in more time critical environments. I believe that there's a little bit more latency though, because it does kind of a check and a handshake to make sure that everything's in sync. So NTP provides time synchronization within milliseconds, suitable for most applications where sub-second accuracy is sufficient. PTP offers much higher accuracy, achieving synchronization within nanoseconds or even picoseconds for time-sensitive applications like high-frequency trading or scientific research.
Stock market, maybe? Interesting. Yeah. And so Josh mentions that Dante uses PTP to be very precise. Yeah, because in video, we don't really care, right? If we lose a frame, no big deal, right? It's just a blip. But if you lose audio, that is critical because people will tune out very, very quickly without good audio.
Right. NTP, in my experience, is hosted by, the U.S. Naval Clock and things like that. And it's probably how your touchscreen gets the time in its corner. PTP would be what devices on a network use to synchronize with each other and make sure that there's no clocking issues with things like Dante and some of these codecs that we rely on.
Got it. So this is a good segue to security. Everything that's sent over the network is in clear text. That's true on HTTP, like I said. This includes any information that you put in a site, like your email, your address, your banking information, your social security number. Don't send stuff in clear text. We were talking before the start of this of a friend of mine that got hacked on Facebook, and they were selling a bunch of stuff, and they took over his Facebook. So probably simple password, not multi-factor authentication. Hackers got in there and took over his account. Not that easy to get control back either. HTTPS is a protocol that encrypts the information, and so therefore it can't be read. SSL, secure socket layers, will ask the website for a certificate to authenticate the identity of the website. Once communication is confirmed, then the content can be transferred between the two. TLS, transfer layer security, is like SSL. It authenticates the website and the data between the computer and the website. TLS is a new version of SSL, but we still call it SSL certificates because TLS just replaced the older versions. When you combine them and other protocols of the version, you get basically HTTP turns into HTTPS, FTP plus TLS becomes FTPS, and so on. Now let's review some of the network hardware. You have switches that collect the MAC addresses and connections between the devices. Most often these switches are referred to layer 2 switch or layer 3 switch. Often, insisting a layer 3 switch is necessary for a multicast network to function properly, which is what AV over IP is a multicast. Remembering the OSI model, layer 2 refers to the data link layer, layer 3 refers to the network layer. As such, a layer 2 switch is one that performs switching on the data link layer using MAC addresses. A layer 3 is one that switch it on the network link layer or the IP address. Another easy way to understand this is to rate the terminology is layer 2 is the switch, layer 3 is the switch plus a router. The router we mentioned earlier literally routes the IP address and packets being sent. Routers can also work in a hierarchy, as one router can control the behaviors of the routers beneath it. This gateway is the topmost router. As a bridge, connects the two different networks. And an example of this is a broadband modem. This model converts or bridges the Ethernet protocol to a WAN protocol from your house out to the internet. Finally, there are access points that allow for a wireless network. Some devices can act as an access point in an AV system. Think BYOD. All right, let's switch gears again. Mention the IP addresses that were on 192.168.1.255 could be used as a broadcast. But what does that mean? You see, there are different types of network traffic: unicast, broadcast, and multicast. Unicast is a one-to-one transmission with two options. UDP, best effort. TCP is transmission control protocol, means all the packets are received completely in order. UDP, user datagram protocol, this is connectionless. This means there's no guarantee that the other side will be ready or to receive everything in the correct order. Broadcast is one to all. That is based on the layer 2 and therefore not routable over different networks. In other words, it's locked to a specific VLAN. The other is direct broadcasting, which allows one device in the network to transmit to all the devices in another network. Multicast is one we use in AV over IP, and that's the communication over that network. Destination nodes send IGMP, Internet Group Management Protocol, join and leave messages. For example, in the case of AV over IP, when the user changes from one source to another, that's basically a leave message and then a join message. Multicast easily scales to a larger receiver population by not requiring prior configuration to identify or register the receivers, since they individually joined the multicast group. Multicast uses network infrastructure efficiently by requiring the source to send data packs only once, even if they need to be delivered to many receivers. The nodes also think as devices in the network can take care of replicating the packets to reach multiple receivers in the multicast group.
Remember here too with IGMP, Jeff Levesque had mentioned it, and so did John Schrenker in his session. That's when we talk about querying and snooping. So querier, more properly, excuse me. It's kind of like the traffic cop for your multicast traffic. It's looking at who's sending data, who's receiving data, and making sure that those groups all align. Snooping is the communication protocol that they negotiate all of it with the querier through. So those terms go with this if you were remembering them from a past session.
The other thing to keep in mind is PoE, PoE plus, PoE plus plus, all different power. And why this is critical is when you're doing network design, right? Because you need to know what your device is, how much power it's going to consume, because it could drastically change how you want to configure the network. PoE allows 15 watts, PoE plus allows for up to 30 watts, and PoE plus plus could be 60 watts or 100 watts. So the best thing to do is actually look on the website of the device, look down in the specifications. Sometimes it's buried. Power, very power.
That's not on the screen we can see, Steve.
Oh, thank you. Multi-screen is awesome. All right, yeah, so this one, PoE, 12 watts. So let's take, for example, this Netgear switch. Inexpensive managed switch, 8 ports. Look down at the specification, 110 watt power budget. Make it a little bigger so you can see it. All right, so then I go and bring in the handy dandy calculator. 8 times 15, 120. Whoops. It's only 110. So you better make sure that one of your devices doesn't need PoE or powered externally. And it would be really bad if you needed PoE plus. Whoops. 8 times 30. Now we're way over the power budget. So it's not just network ports, it's also the power for those ports. All right, AV encoding allows for the transmission of audio video content over the network. more efficiently. Encoding is the critical as it encompasses the raw video, which reduces the bandwidth. Decoding is completely opposite, the process of uncompressing the encoded video. The encoded streams are converted into HDMI to be displayed. As we begin to put our AV content and control on the network, we need to understand bandwidth is also important. We looked at the power budget, now we're going to look at the bandwidth. For our products, it's configurable, right? But general rule of thumb for 4K 60 444 is going to be a gig or 900 meg. So you want to use 900 meg plus an overhead budget of 10%. Whoops. Oh, there we go. I'm missing a slide. Sorry about that. Okay, so on a single switch, all you really need to do is worry about the PoE budget. When you start to get into multi-switch, then it depends where the encoder and decoder lie. As Jim mentioned, the courier is going to be on the lowest IP address, and it's going to be on one of the switches. It can't be on two. What the courier does is allow that subscribe and leave. But the encoders are where you want the courier. So in this example, we'll say that we have 12 encoders and 20 decoders. The bandwidth needed between the switches is calculated by the bandwidth of each encoder plus 10%. So in this example with 12 encoders, 20 decoders, I put all the encoders on the first network switch. It's roughly 12 gig. So my link cable between these two switches and these switches both have to be capable of doing a 20 gig link. So what happens when I need the encoders on a second switch? Maybe they're in a different room or different part of the building. For example, we'll keep with the same count of encoders. We'll go with 12, but now we'll split it between two switches. 3 on the first switch and 9 on the second switch. Since the courier is on the first switch, we have to account for the encoder traffic going to the courier and back. So 3 meg for the first switch and 18 meg for the second switch. Sorry, gig. So now we've got 21 gig between those uplinks. That 2 uplinks isn't going to work anymore. Now it's going to need to be 3, or we're going to need to switch the courier. Basically, the one that's got the most encoders is where you're going to want the courier on a 2-switch system.
Everybody see how the encoder here, oh, sorry, Steve, it's sending its traffic back to the courier. So you don't only have traffic leaving from switch 1 to switch 2. You've got that traffic from the encoder coming from 2 to 1 before being resent again. You multiply what goes through your uplink by doing that. So that's why you want the courier closer to your encoders, and if you can avoid it, don't have encoders further out towards the leaf nodes of the system.
Also make sure these are static IP address, because if they're DHCP and they suddenly lose power over the weekend, they can change who's the courier. Ask me how I know.
Election processes.
Now, when we get to multi-switch, or where you're doing it fully converged, it kind of gets a little more complicated, because you have to count for not only the encoder traffic like we were counting before, but now it's also the decoder traffic, because you have to count for this traffic being the source, but also the destination, because here we've got up to 3 decoders. So literally I could have up to 3 coming out, and it could be these 5 are being sent to this other switch. So when you're calculating multi-switch, you have a core switch for the courier. When you're calculating this bandwidth, count both the encoders and the decoders. Questions?
Does everybody feel cozy looking at a chart like this, or is this above and we need to rephrase and draw lines and do some annotations? Feel free to throw reactions or put questions in the chat, anything like that. All right.
Well, I hope it was helpful for those that are completely new to networking. This series will continue. We're going to have, like Jim said, the same Thursday, same bat time, same bat channel, I believe it is, every Thursday for every 3 weeks until now, till the annual conference.
Yep. An upcoming session will be about Dante and technologies related to that, some of the specificities that you need to plan for in those kinds of networks. We're going to have another session that we hope can dig deeper into clocks and election and some of those things that turn into the issues that a lot of us end up troubleshooting when we do systems like these. And then we've got SDVOE and things like that that are penciled in later if we can find somebody that speaks to that, and it makes it good continuity with the rest of the series. So we've got some great plans for the next several sessions. So,
and if you've got a topic that you would like for us to cover, feel free to contact myself or Jim. We'd be happy to fit it in before the annual conference, or maybe we have a workshop during the annual conference to delve into deeper topics.
That's a conversation we should have. Absolutely. Last call for questions. If anybody's got topics that they want to see a slide again or hear a different explanation or anything like that, please let us know. All right. Well, thanks so much, everybody. Watch for an invite for the next session in 3 weeks, and reach out about anything and everything between now and then. We'll see you later. Thanks again, Steve. Good session.
Thanks.